Today we're talking about similar figures. Again, remember you take the notes. I will be checking them off on Monday in class. So with similar figures, we need to be able to handle proportions first of all. So we need to make sure we know what a proportion is and how we solve it. And it is something you should have seen before. Okay, a proportion is two ratios equal to each other, basically two fractions equal to each other. And we can have any combination of letters and variables that we want. So if we have a proportion like that, the way we solve it is to cross multiply. When we cross multiply, we take the bottom of one side, multiply it by the top of the other side, bottom of the right, multiply it by the top of the left. And when we multiply, this 7 has to multiply by the entire thing, x plus 5. So if you remember to multiply it by both, you don't have to write out the parentheses, but it can be super helpful. And then x times 3 is just 3x. So we have to distribute this. 7 times x is 7x. 5 times 7 is 35. And then we have to finish solving this equation like we've been doing with all of our geometry. These all boil down to usually some fairly similar type equations. So we want all the x's together, which means I want to minus 7x from both sides. So I can get all the x's on one side. We get 35 equals negative 4x. And we divide both sides by that negative 4. 35 divided by negative 4 is negative 8.75. So again, solving a proportion should be fairly familiar to you. So we need to know about our proportions so that we can talk about similar figures. When we talk about similar figures, they are two shapes that are the same shape but different sizes. So similar figures have the same shape but different sizes. And we show that two things are similar by using, instead of the equal symbol, just the squiggle at the top of the congruence symbol. Would say these two triangles are similar. That's what just the squiggle means. So we want to be able to tell a couple of things. We want to tell if two shapes really are similar, and we want to find missing sides if we know some of the sides but not all of the sides. So for two shapes to be similar, they have to be enlarged by the same amount. For example, if we had a square, we knew each side was 2 inches of this square. To make a bigger square, so same shape, still a square, but different size, we'd have to multiply both of those by the same amount. I'd have to multiply both by 5 to make it 5 times bigger. So we'd have 10 and 10. If I changed and said only 2 times 4 on one of them, I'd get a rectangle instead of a square. It'd change the shape. So we've got to be able to check that we multiplied by the same amount to see if those two ratios are the same. So let's say we have a kite. We have these two sides are 3, these two sides are 7. And then we have a bigger kite. These two sides are 6. These two sides are 15. So we want to see, are those shapes actually similar? Are they the exact same shape, or did one of them get changed a little bit? So our instructions are state if the polygons are similar. So for each corresponding side, we need to make sure they got multiplied by the same amount. So if I look at the 3 on the top right there, and I say, well, the side that's the same is that 6 over there, I want to divide those two values and see if it's the same as all the rest. So I want to see if it matches what we get when we divide another set of corresponding sides. We'd also have to check the bottom two sides. We need all 4 sides to be changing by the same amount for this to work. And then the last two sides, the 7 and the 15. So we've got to check and see if all of these fractions are the same. We can reduce 3 over 6. We can divide both of these by 3. They were the same for these two sets, so I'm only going to write it once this time. We know really that's both of those are just 1 over 2. What about 7 over 15? Is there anything we could divide into both 7 and into 15? We think about it, and there's not, so we have to leave this as 7 over 15. So it's close. It's almost a half, but it's a little bit over. So these shapes are not similar. If the two values didn't match, or maybe you have to do more values because it could have 3 or 4 different sides instead of just 2 different sets, then this shape is not similar. Let's do one more example of this. Let's say we just have some triangles. This is 3, 4, 5. And that is 6, 8, 10. So again, we're trying to prove that these are similar or not. Maybe they're not. So we need to make sure the ratios are the same. But notice the triangles are no longer in the same orientation. One of them's been turned a little bit. So we've got to identify what matches with what other piece. So when we look at this, we know 3 is the smallest value on the first triangle, so it's got to match to the smallest value on the second triangle. So 3 over 6 go together. We have to check that ratio compared to the next one. I can pick whatever I want for the next one. 5 matches with 10 because they're both the biggest values. So we have to check 5 over 10. 4, then the only thing left is 8. So that matches 4 over 8. And now we have to reduce each of these fractions to see if they're the same. The first one can divide by 3, which gives us 1/2. The second one can divide by 5, which gives us 1/2. So far, we're good. And then we divide both by 4, which also gives us 1/2. They all match. So these two shapes are similar. They are the exact same shape. Just one has been made bigger, and it's been rotated around some. So the second thing we need to worry about is what if we already know they're similar, but we only know parts of the information about the sides. We don't know all of the information possible about the sides. Say we have a rectangle. We don't know what that first side is, but we know the second side is 10. The instructions will say, find the missing length, or find the missing side length. So then we have a second shape. And actually, let's rotate it just to practice what it would be like if it's rotated. Let's say this is 4, and this is 22. So if we're going to find the missing side, we've got to set up that same kind of ratio we did when we were proving they were similar. But when we try and put something in the question mark spot, we're going to have to replace it with an x. We're looking for that side, so we need a variable to hold its spot.
Please report to room 217. Thank you.
Sorry about that. So we take the two pieces from the one triangle and stack them over each other. But then when we go to the other triangle, we've got to make sure that we pick the same sides in the same order. We went from the small side first to the big side second. We went x over 10, small to big. Well, we have to do the same thing on our other rectangle, even if it's rotated. So we need to say, okay, what's the small side on the big rectangle? That'll be the 4. What's the big side on the big rectangle? That'll be 22. So once we've set up our proportion, now we just solve it with cross multiplication like we reviewed at the beginning. We multiply 22 times x, and then we multiply 10 times 4. So 22 times x is still just 22x. 10 times 4 is 40. We still have to get x completely alone, so then we have to divide both sides by 22. So we plug that into a calculator. Oftentimes with proportions we end up with decimals. So that would give us 1.8. So our last example is maybe we have a shape and A, we might have more information than we need, and B, maybe they have x plus something instead of just a plain old missing spot. So last example. Say we have a trapezoid. This is 3, this is 4, and this is x plus 5. And then we have a bigger trapezoid. This is 6, this is 8, and this is x. So we still need to set up our proportion. But we have 3 sides, and to set up a proportion, we only need 2 sets of matching sides. So we want to make sure to always pick the set of matching sides that contain the x's. So I have to pick the x plus 5 because I am going to be I'm trying to solve for x. I need x in my equation. Then I can pick whichever one I want. Let's pick 4. So we start setting up our proportion. We have x plus 5 over 4. Now again, we have to make sure it matches the sides on the other shape. X plus 5 was kind of the top of our trapezoid. The right trapezoid has been rotated, but still the top of it is the variable x. Then we have to make sure we pick the correct second value. We picked 4. 4 was the bigger of these sides going down. So on our sides going down on this one, even though it's been rotated, we want to pick the bigger value, so we need to pick 8. Again, once we've set up our proportion, it's all down to cross multiplication. If we can match up the corresponding parts, then we multiply. So first we have to multiply 8 times x plus 5. Then we have to take the 4 and multiply it by x. To simplify this, we would have to first distribute the 8. We saw problems like this where we had to distribute when we were doing mid-segments of triangles. So 8 times x gave us 8x, 8 times 5 gave us 40. On the other side, 4 times x is just 4x. Now again, we plug stuff back in, or not plug stuff back in, sorry. Now we use our opposite operations to solve. So first we do the opposite of our x's, and we want to get our x's to the same side. So I minus 8x from both sides. And then I would do my opposite of negative 4 times x. So I would divide both sides by negative 4. So enjoy your weekend, and I will see you guys on Monday.